Hello, we are Team 4. We have chosen the paper Dream to Control Learning Behaviors by Latent Imagination. This paper was presented at ICLR 2020. Dreamer is a model-based reinforcement learning algorithm where the training objective is to learn a model, also known as a world model, and learn value and actor networks trained on the future prediction of the world model. The trained actor network then interacts in the environment. I like to think of the world model as a nonlinear state estimator and the actor policy as a nonlinear optimal control law. Focusing on the world model, we can intuitively think about it as our brain, where we can imagine and predict how the world changes and evaluate how valuable those future positions are based on some sequence of actions. The world model consists of an encoder that compresses the RGB image into latent space, a reward network to predict the reward for this state, a transition dynamic network that predicts the next latent state conditioned on some action, and a decoder that reconstructs the RGB image from the latent embedding. Predicting in the compressed latent space is more computationally efficient than in image space. This allows us to predict thousands of future sequences parallelly on a single GPU. We can then decode the latent prediction into RGB space as shown in the figure below. We learn a behavior policy through an actor-critic style of learning, where the agent learns a value network and an actor network via backpropagation of the predicted rewards and future latent state. This tells the agent how its current action affects the future predicted rewards. This is very similar to how a human would imagine good and bad scenarios and would evaluate different actions in their imagination. Dreamer has several limitations. Learning an imperfect world model during early learning stage can result in improper planning and policy. Thus, the samples collected would be limited to the poor interactions in the environment, and the agent learns a locally optimal solution. Furthermore, Dreamer's world model uses a gated recurrent unit (GRU) to model the transition dynamics. And as we know, GRUs and other RNN-like model architecture suffers from long-term memory loss. Additionally, reconstructing the image could be considered to be computationally ineffective, as there might be no need to reconstruct irrelevant visual signals. For example, there is no point in learning the color of the floor, as probably it does not help any way to plan. We also suspect that Dreamer might struggle in sparse reward tasks. For related works, Planet was the predecessor of Dreamer, where they used similar world modeling with MPC to plan in latent space. However, they found MPC to be computationally expensive. Dreamer v2 succeeded Dreamer v1 and changed the latent space from a Gaussian latent to a discrete categorical latent. This led to the world model to reason in terms of discrete concepts for accurate prediction. Daydreamer implemented Dreamer v2 in the robotics domain, learning complex behavior such as a quadruped's walking gait just in 1 hour, using only one agent interacting directly in the world without a simulator. Dreamer v3 improves Dreamer v2 by stabilizing the learning by using techniques like normalization, balancing, etc. Dreamer v3 is very robust and can solve various tasks without hyperparameter tuning.
Then we will explain about why we choose Dreamer. The reason we choose Dreamer over other robotics papers is practical usefulness. Leading companies in autonomous driving and AI research are adopting world modeling to better understand the world and implement naturally human behavior. In model-based reinforcement learning, like Dreamer, the world model predicts changes in the environment and use planned actions to achieve its goal. This goes beyond simply leading to the present situation by considering long-term values and reward. As a result, it can mimic human-like control, which we believe is crucial for complex real-world applications. Moreover, learning a world model provides the agent with a general understanding of environment. This enables quick adaptation or performance improvement in new tasks without having to learn from scratch. This aspect strongly resonated with us. We plan to conduct experiments to test how well our improved Dreamer generalize across different scenarios. Additionally, Dreamer has demonstrated superior performance compared to traditional model-free agents, making efficient use of data and requiring relatively less training time, which align well with our project. The fact that it is open source and includes various improvements, which we had discussed, and this is our replication plan. Since we are all new to Dreamer, we will review the existing open source codes for version 1, version 2, and version 3 to track the key technology changes. Ultimately, we plan to rebuild and retrain the model based on the latest Dreamer version 3. Additionally, as shown in the second image above, Dreamer version 3 has been tested across diverse visual domain with for test case. We will verify whether our improvements are beneficial by comparing in the control2 environment. Secondly, the reason we choose this topic it is we believe it would be useful for real-world applications. For therefore, it is important to assess whether our improvement can be applied to complex robotics test case. To evaluate this, we plan to compare the performance of our improved model with other model-based and model-free algorithms using humanoid bench. Humanoid bench consists of 15 test cases such as powerlifting and packaging and provide a diverse observation environment. The observations include four attributes: robot state, task-relevant environment observation, egocentric visual observations, for body tactile sensing. We will adapt our improved Dreamer version 3 to this environment and conduct experiments to evaluate its performance.
So in this section, we will focus on the improvements that our project aims to achieve. The main improvement we want to make is the use of curriculum learning. As a reminder, this is a technique aimed at gradually increasing the model's training difficulty. The model is not trained directly on the task for which it was designed, but on a succession of subtasks of increasing complexity. There are several advantages to using this technique. Firstly, it enables good performance to be achieved more quickly than with conventional training. Secondly, it allows better convergence with guided training, which avoids convergence toward local optima. The main challenge of this technique is to define the concept of difficulty and how to evaluate it in order to compare it on task. A second idea for improvement consists of implementing secure exploration by means of constrained reinforcement learning. The main interest will be to prevent the agent from reaching damaging or costly states. This idea is particularly interesting in the case of real, non-simulated environments where certain actions could be harmful. The inspiration from this idea comes from the Daydreamer paper, in which the Dreamer model is used directly on robots in real-life conditions. In limitation section, this paper highlighted the fact that the training often required human intervention to avoid dangerous states, and that it led to a lot of robot repairs. Some solutions, such as CPO, could be considered. If time permits, we can mention a final improvement which consists of directly modifying the structure of the model. Models such as GRU or LSTM are currently used. The integration of more powerful architectures such as Mamba may be relevant for improving performance and accelerating the learning process, particularly in terms of memory management in order to prevent memory loss, for example, but it can also improve exploration and sampling of experiences. Mamba combines the advantages of models based on memory networks and techniques for modeling environmental dynamics. And now I'm going to present the timeline for our projects. The first task on which we want to focus is the replication of existing experiments. We expect to spend 3 weeks on this. The second task we want to prepare for the next presentation is the implementation of the first improvements using the curriculum learning. Finally, the last two improvements will be carried out at the end of the semester, particularly the last improvements which will be carried out if time permits. That's the end of this video. Thank you for your attention and don't hesitate to contact us if you have any questions. Thank you.